So what we're gathering from the last couple examples is that there are some laws for probability, rules for probability that cannot be violated. And so we are seeing that, first of all, that every probability for an event must be greater than or equal to 0 and less than or equal to 1. In other words, all probabilities have to be between 0 and 1. Nothing can be higher than 100%, nothing can be lower than 0. And then we are also seeing that the sum of all the probabilities must be equal to 1. That if you add up all the outcome probabilities, or the probabilities of every outcome in a sample space, that total must make 1. Let me back up to another example just a minute ago. In this example, example 3, we saw that the probabilities here summed to 0.999, and we were a little bit worried about that at first, but then we realized it was due to rounding error because we were rounding each probability to the third decimal place. But in general, the sum of all the probabilities for a sample space should be equal to 1. This leads us to a couple other truths, namely that if an event is impossible, so something that could never happen. So for example, the probability that the Lions will ever win the Super Bowl. I'm just kidding. Of course, I'm from Michigan, so we just kind of accept that the Lions will never win. No, I'm just kidding. Some people really hold out hope still. So an impossible event. So the probability that you'll get, I don't know, a negative 10% on an exam when the scores are between 0 and 100. You can't get a negative 10%. Or a certain event is something that it will definitely happen. So something like, I don't know, the fact that the probability that the Yankees will win the World Series again. Sorry, I almost said Super Bowl. And so of course we don't know for sure, but we can take a guess based on past experience that the Yankees will win the World Series at some point. But I'm joking. The probability that the sun will rise tomorrow. Again, not 100% technically, but really close. So those are all certain events. So an unusual event, and this will kind of come back to haunt us later on in the course, but for now we're going to define an unusual event as anything that has a probability that is less than 5% or less than 0.05 for the probability. So anything smaller than 5%, that's considered unusual. So keep that in mind later on. And that should look familiar to you because we defined it that way back in chapter 3 as well. When we talked about the empirical rule with standard deviation, we mentioned that 5% or less was unusual. Some books say that 1% is very unusual. So, now, a probability model is, well, there are a lot of ways we could do this, but basically you want to list out all the possible outcomes with their associated probabilities. Now, the easiest way to do that is a table, right? To construct a table and have it have the possible outcomes and the associated probabilities. So our first mission is to determine whether or not the following are valid probability models. Explain. So we're going to look at these, and remember, we don't really care what the outcomes are. What we care about is the probabilities. The probabilities have to abide by both of these rules. Right? So they both have to come in play. So let's look at the first one. These are all between 0 and 1. Yay. That's good. No negatives, nothing bigger than 1. And the sum of them, well, let's see, this is 5.5 plus 0.1 makes 0.6, and that's 0.4, so that makes 1. So this one is valid. This one over here is not valid. It adds up to a little bit too much. So that would be not a valid distribution because it adds up to 1.1. And that's what I just wrote there. So you have to mention both things. Every probability is between 0 and 1, and then the sum of the probabilities is equal to 1. So this one is valid. The one on the right is not valid because even though the probabilities are between 0 and 1, the sum of the probabilities is not 1. Now remember, if it was like 0.999 or something like that, then that wouldn't be so much of a problem. But for these, there's no rounding here. It's not working out nicely for us. All right, now what about this example? So these are both valid probability models for the genders of 2 children. I should say the biological sex, but I'll fix that for later. So we have these 2 separate tables, and they are showing the same distribution but in a slightly different way. So this particular one considers biological sex. So it could be male, 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 female, female, male, female, female. And these are the associated probabilities. This is assuming the biological sex is a 50-50 split, which is actually not the case. When you take a biology class, you find out there's a little bit more complicated stuff going on right there, but we're just going to pretend for right now that it's 50-50 male-female. So that gives you a 1 out of 4 chance for each of these 4 combinations. And this combination over here kind of pushes together a couple different ones. So it takes the male, female, female, male mix and it mushes it together, if you will, with the number of girls over here. There we go, I color coded them. So you could see male, male means you have no girls. So that would be 0.25, whereas male, female, and female, male both mean you have 1 girl. So that would be here, and together they would make 0.5. And then female, female is 2 girls, so that's 0.25. They're both completely valid, but they're kind of viewing it in a slightly different way. Right, so the one on the left is actually more of a chapter 5 way of viewing things. It treats the individual outcomes as separate, and the one on the right is kind of grouping things together, and that's more chapter 6. There, and I just typed that up. So the chapter 5 side of the house kind of considers each outcome separately. And then the chapter 6 kind of groups them together for the sake of convenience. They're both valid. There are times where we're going to want one and times where we're going to want the other. In particular, in chapter 5, we're going to want the one on the left more. And then once chapter 6 rolls around, we're going to want the one on the right more. Now, if we're going to have to create tables like the one on the left, it is often helpful to construct a tree diagram to help organize ourselves and figure out which are the appropriate outcomes so that we can make a list of them. So a tree diagram is just a graphical organizer that helps us figure out the way to list all these different possibilities correctly. And for simple experiments that don't have a lot of outcomes, it works fine. It's not everybody's favorite thing to do, but it'll work great. You don't want to do it for very large experiments, and we'll see why. All right, so I have a very, very simple example right over here on the right, where we have the head and we have the tail. There's the beginning of time at the circle. So the circle on the left represents the beginning of time. And then you have the arrows going out towards head and tail. Those are called branches. And then the outcomes are listed over on the right. And you have to make sure that it's vertically listed. Time moves from left to right on the diagram. So time starts at the circle on the left and kind of branches, if you will, called a branch, branches towards the right side, right? So time is moving, you're kind of thinking into the future. So you always start your diagram on the left, move your way to the right, and you want to write your list vertically on the right. All right, so suppose we are going to have 2 children in the future. Pretend you magically know that. What will be their biological sex? Okay, so we are going to construct that sample space. Now it's important that we start at the left, we work our way right, and that there's a vertical alignment going on here. So 1 second. And there you have it. So I start with the green arrow. I start over here on the left with the green arrow. And then, not to be confused with the comic book character. And then I move my way to the 2 possible outcomes, and they are vertically lined up. The M is over the F. So that's the first child, that green arrow set. Then there's the blue arrow set, which comes next. That leads to M, F, or M, F. This means that I've created a sample space. I could go top branch for the first one, and then top branch for the next one. That's M, M. So I write M, M over here. I could go top branch for the first one, then second or lower branch for the second one. That leads to M, F. Or I could go lower branch and then upper branch, so that's FM, and then lower branch, that's FF. Now the assumed probability for each of these outcomes is 1/4 because you assume that male females are equally likely, 50% chance for both, etc. Again, if you take a biology class, you learn that that's not quite a fair representation of everything, but we're just going to assume it. We're going to assume right here, it says assume equally likely. So we will assume equally likely right here, 50-50 shot. So we'll see why this is later, but 50 times 50, 0.5 times 0.5 makes a quarter, 0.25. In other words, if you look over here at the sample space, there are 4 equally likely outcomes. All right, now let's define event H as having at least one boy. So all they want us to do is define it. That doesn't mean I'm finding the probabilities for it. Notice, warning for notes and other things. Sometimes we just want you to explain what it is. So having at least one boy means you're having one or more males. And that means that you're having male, female, female, male, or male, male. Those 3 outcomes represent having at least one boy. All right, is that a simple event? Well, a simple event, let me go back to the definition for that. Right here, a simple event is an event with only one outcome, back at the beginning of this section. Right, so only one outcome, only one possibility. I'll flip back to our problem now. Well, looking here, we would definitely say no, right? Because there are 3 outcomes that would have this. So it's not just one, it's 3. So let me write that. There we go. Just on a side note real quick, that at least business is going to come back a lot. So let's take a note of it right now. At least actually means the same thing as greater than or equal to. So I'm going to make that pink. The words at least are going to show up a lot in chapters 5 and 6, and actually 7 as well. So at least means more than. I want at least one male. That means one male or more, right? Okay, so we said this was not a simple event. Now I'm asking what's the probability. So be careful. A lot of students confuse defining, which literally means write it out. What are we saying it is? So we're saying one or more males, right? Quote unquote. That's defining, right? In words. Whereas P parentheses H, capital P means probability. So you're looking for the probability of that event. And that would be 0.75 because there's 3 equally likely outcomes. Male, 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 female, female, male. All 3 of those outcomes are equally likely, so it's 3 out of 4 for the probability. And there's that. And you can write it as a decimal, percentage, fraction. It doesn't really matter. In the end, decimals are probably what we use the most often. Okay, now last bit. The tree diagram worked okay for 2 kids. No problem. But would you want to do it for 6? And the answer should be a giant no. No, you would not. So the tree diagram would be so large, and I wrote down what it is, and I'll explain that in a second, that it would be difficult to fit on the paper. So we'll need another way to tackle classical probabilities for large sample sizes. And that's where the multiplication rule will come in handy for us. Multiplication rule, both in section 5.3 and actually right now in another page. There, both this section and 5.3 for larger ones. All right, now where did I get it with this 2 to the 6 business? So think about what happened here. We had 2 genders possible, 2 biological sexes possible, and we have 2 children, right? So each time you branch off, there's 2 outcomes, 2 for the first option, first child, the green arrow set, then 2 more for the blue arrow set. 2 times 2 makes 4. But if you were going to have more children, they would keep branching from there. And every child, you have 2 more outcomes. So it becomes 2 times 2 times 2 times 2 and so on. 6 times because you're having 6 kids, right? So 6 children are here. So if you're going to have 6 kids, you'd have to have 2 to the 6th branches. And that's no fun for anybody because that means you'd have to fit 64 branches by the end. And you'd have to have 6 layers to get there. You still have to start at that same green V right here. You start at this green V of 2 and you branch out from there until you got 6 trials over and would have 64 branches by the end. In other words, it would be ginormous and nobody wants any part of that. So we're going to use a multiplication rule to solve that. Now, the probability multiplication rule we'll see in 5.3, but we'll see the multiplication rule of counting in just a video, actually the next video. So I'll see you back here then.